Last time we discussed about correlation. Can you all see the slide?
Yes, sir.
Can you all see the slide? Yes?
Yes, sir.
Okay, right. Last time we stopped at the correlation, all right? We discussed about correlation and we said the correlation, linear correlation, we can talk about in terms of the strength, right? Strength of the relationship, which is meant by the correlation. So we have seen some of the graphs of the correlation, how it could be giving the strength by visually. So on the right side, we have a weak relationship, whereas in the left side, we have very high, strong correlation. So meantime, we can say no correlation between the x and y if the beta 1 is parallel, or beta 1 is equal 0. That means the regression line is parallel to the x-axis. So we can calculate the correlation, or it is the sum square of cross product x and y divided by square root of sum square of x into sum square of y. We have calculated the correlation of the previous example, right? So I think this may be the last point we have stopped. So we can find out the correlation, and based on that value, we can say whether it is having a very high or strong correlation, and the direction. We can talk about the direction of the correlation as well as with the strongness of the correlation. This is where we stop. Now I ask you to find out the value of correlation for the second example also, which is already there. It has a very high correlation. So again, there is a strong correlation. Right. Now we will start from here. In a simple linear regression model, we have two parameters to be estimated, beta naught and beta 1. So as you all said, the beta 1 is the slope and beta naught is the intercept. All right. So this is the fitting of a model for any given point, which is away from the linear line or the regression line. Okay. Yeah. So you want to increase the volume? Just a second. How about now? Can you all hear? We'll have to answer. Can you hear me now?
Yes, sir.
Right. Okay. Right. We will go to the screen share. Right. So this is when you talk about the model, right? When you talk about the model, this is the model for each and every observation. Then we want to predict these two values, which we have already seen. And also we want to test whether beta 1 is equal 0 or not. Right? So beta 1, if it is 0, we could say no linear relationship. Beta 1 could be greater than 0, or beta 1 could be less than 0. These possibilities are there. So then we can say there's a linear relationship. So here, no linear relationship. here there is a linear relationship, right? So this is what we want to test it now. For that, we want to understand a principle on. Let's take. I'm going to take similar pot plants of 16. Similar pot plants of 16. That means all the management, all the genetic material, everything is same. So identical 16 plants, right? So identical 16 plants will be taken. So identical 16 plants will be taken. Sorry. Identical 16 plants will be taken. All these 16 plants are in the pots. So you have 16 pots, right? Now I want to do a small trial applying fertilizer. So I have 4 treatments. What are the treatments? 4 treatments applying 5 gram, 10 gram, 15 gram, and 20 gram. So I have 4 treatments that I'm going to apply. So since I have 16 plants, I can allocate 4 plants each for these treatments, right? Equally, I'm going to allocate 4 plants each to all these treatments. So altogether we have 16 plants. So initially, before applying the treatment, before applying this fertilizer, different amount of fertilizer, all 16 plants are in a similar condition. No difference at all. No difference at all, right? So that is the condition. Now I'm going to see their results or in terms of yield. So I'm going to measure their yield in a pot, right? Treated with 5 gram, 10 gram, 5, 10, 15 gram, and so on, right? And 20 gram. How many pots have been treated with 5 grams? How many pots have been treated with 5 grams?
4
4 pots.
pots.
Huh? 4 pots treated with 5 grams. Again, 4 pots treated with 10 grams, 4 pots treated with 15 grams, and another 4 pots treated with 20 grams because we have 16 pots. Initially, all these pots are same. Right. My question is now I have treated 4 pots with 5 grams. Let's look at that first. For 4 pots, all right, with 5 grams. My question is whether all these 4 pots will give the same yield or will they give the different yield?
Different yields.
Why different yield? What is the reason? Why all 4 pots will give different yields?
Performance of plant will be varied due to other reasons
What,
beyond the fertilizers.
what is the other reason?
They are genetical factors.
Because I already said that all are same genetical factor. They are
Time of the application.
time of
Application.
same. Amount of water that I am pouring is same. Weed management is same. Everything is same. Everything is same. Now, what is the reason for this difference? You see, there's a difference among these 4 pots. What is the reason? Similarly, if you go for the second treatment, gram 10, 15, and 20, again they will show the same deviation. So that you don't get 1 point. All plants will not give same yield. But we said that initially we took all similar condition plants. As you all said, genetically, environmentally, management, everything is same. Right? So you see the variability of this yield. Plants treated similarly, plants, because these 4 plants are treated similarly, isn't it? All give same amount of fertilizer, uh, treated similarly. Everything is similar, but they show the difference in yield. This is, we cannot explain. We can't explain. So in other term, only God knows, right? So we can't explain the variation between the plants which has been treated similarly, right? Better to don't send a chat, you'll have to answer it. Huh? Maybe sound is not clear. Now something wrong with your system, because here I have given all the support. I have increased the volume as well. Something wrong with your system. Check with your system, right? Yeah, your connectivity. Look at your connectivity. So we can't explain the variability of this. So another term, we can't explain the variability of that, right? So the variability between the plants which are treated similarly cannot be explained. But if you look at the variability in this direction, what is happening? Look at here. The yield is increasing, isn't it? Look at here, the yield is increasing. So why yield is increasing in this direction? Because if you take the average, yield is increasing. So that we could say, if you increase the amount of fertilizer, the yield is increasing. So here, when you talk about the variability in 2 dimensions, 1 dimension is in this x-axis, along the x-axis. 1 dimension is along this y-axis. If you look at visually, the increase in along the x-axis, why? It is because you are increasing the amount of fertilizer. That is obvious. When you increase the amount of fertilizer, the variability increases. But along the y-axis, what is happening? For a given x value, the variability increases, but that variability we cannot explain. So we can explain this variability, but we cannot explain that variability because for a given x value, the yield are different, so that we cannot explain that variability. So the total variability given by y can be partitioned into 2 components, right? So that is, one is called as explained variability, the other one is called as unexplained variability or the error. Can you remember in the model we have including a term E, error. So this is what we call as error. Okay, so in a model, can you remember this model? We talked about this and this. We didn't talk about this much in earlier. So this is what we call as error term. So error term, right? So this is what we are explaining. This error term is actually a kind of deviation which we cannot explain, right? So the total variability in y can be explained by a part which we call it as due to regression model. So due to regression model, right? Due to regression model. And another part which we cannot explain, which is called as error. Okay, so now we are going to talk about what is this error and how we can quantify this error, etc., etc. Right. In a simple experiment, we have taken 2 points. One point is here, the other point is there. So their respective coordinates have been given, x1, y1 and x2, y2. Respective coordinates have been given, x1, y1, x2, y2. Right? So what is this blue color line? How do you call this? How do you call this? Anyone? Is it the line?
Predictable line.
Exactly, predicted line. It as a predicted line, right? Now we take a overall yield, average yield. So this is the flat form, which we call as overall average yield for an experiment, right? We can take the same experiment. So I'm taking only 2 points. First point is below the predicted line. Second point above the predicted line, just to show you the difference, right? Now, that is the total variability that we can explain, right? This is the total variability. It is from the observed value to the y bar. Observed value to the y bar. Similarly, observed value to the y bar. So that is called as total variability. Maybe in your here, maybe some keys are coming in your printout, handout. It is obvious. It is actually y1 minus y1. Here we have 2 observation plus y2 minus y bar, which is positive, which is negative, which is positive, which is negative. Y minus y bar is a negative value, isn't it? Y2 minus y bar is a positive value. So if you have positive and negative, they have a chance to cancel out. To get rid of that, we are squaring it up. So you can see here, some squares are coming, squaring it up. All right. Once you square it, okay. I have pressed some unwanted thing. Right. Once you square it, we can get rid of right. You can get the square of that value, right? You can get rid of this square values. You see, this is the deviation as I said. So you can get the square of it, right? Then this will cancel out if you don't square it. So that is why we are squaring it. If you square it, then it is not a problem, right? So this is basically called as sums of square. I will come to that. It is how we measure the total variation. That can be partitioned into 2 components. Here, this component and this component, isn't it? So likewise, here also I can partition into this component, this and this. That is what I'm going to show you now. So that can be given for partition into 2 components. One is that component, the black color one, right? So that is called as, that is equal y hat. So this is your y hat. It is the predicted value for a given x value. Huh? This is the predicted value for a given x value. So y hat minus y bar. It is due to our equation. So this is due to our equation. So that variability is due to the equation. Y hat minus y bar is the regression variability. The third one, the green color deviation, that is the last component, which is called as unexplained variable or the error term. we call it as error term. So basically, the total variation in y can be partitioned into sums of square of regression. SSR means sums of square of regression plus sums of square of error. So you can partition into sums of square of regression and sums of square of error. Right? So variation in y can be explained by the regression partly. The other part is by error. So when you say error, this we cannot explain. This we can explain, right? The sums of square due to regression, this we can explain. So total sums of square is due to regression sums of square and the error sums of square. So it has regression sums of square and the error sums of square. Okay. So this further can be given as, this is the total sums of square. This is only for 2 points. I have shown you x1, y1, one observation, then x2, y2, two observation, just for the comparison. So we will have to do it for all the observations, not only for these two observations. Whatever the observation that we have to be calculated. This is the total sums of square, which is rely on the regression sums of square and the error sums of square plus error sums of square. So this we can write it in terms of summation of yi minus y bar whole thing square is equal summation yi hat minus y bar whole thing square. And the last one is the error term, is the summation yi minus yi hat square. So this is what we bring the principle of ANOVA. So first time you are learning this ANOVA, analysis of variance. Maybe once you come to your next semester, not next semester, I think for one, you will be learning more about this ANOVA. And ANOVA is a short term. It is called as analysis of variance. Analysis of variance. So this, how this variance could be partitioned. So the total variation, if you say this is the total variation, part of the total variation can be explained due to regression, right? Part of the variation explained due to regression, and the remaining part is unexplained, which is called as error. Which is called as error. Okay, sometimes it is called as residual or error. So this ANOVA table, this is called as ANOVA table. Mainly, we have few components. The first component is called as source of variance. That is how we divide the different variability. That is the source of variance. Degrees of freedom, we will see that. Then calculation of sums of square. Then calculation of mean square, and at last F statistics. We don't use T statistics here. F statistics. We are looking at the ratio. Right? So here we have source of variance. We can divide into 3 components basically. A regression component, as I pointed out earlier, the total is the total variability, can be explained by this is regression, right? This portion is regression. This portion is error, right? So here one portion is regression, other portion is total. So total minus error will give the answer for error terms on all aspects. Let's look at one by one. Degrees of freedom for regression is 1. So how many variable are we taking in this example or in this study? Simple linear regression, we have 2 variable, y variable, x variable. We have 1, 2 variable. So what is the degrees of freedom? 2 minus 1 always for a simple linear equation. So that you have degrees of freedom 1. What is the total degrees of freedom? N minus 1. In general, total degrees of freedom is N minus 1. The total number of observation is N, so N minus 1. So that what is the degrees of freedom of error? Error degrees of freedom is N minus 1 minus this 1. So ultimately it is N minus 2. Error degrees of freedom is N minus 2. Okay. Then sums of square of regression. This is beta 1 hat square. We found out beta 1, how to get the one of the parameter beta 1 slope, and multiplied by the sums of squares, multiplied by sums of square of x. Right. So this is a formula. You can derive the formula, but you don't need. So this is the formula that we'll have to use to calculate the sums of square of regression. Then we have the total sums of square, that is this one. Then as usual, if I want to find out the sums of square of error, total minus regression sums of square. So this is the total sums of square, this is the regression sums of square. We will see with examples later, right? So this is the regression, sorry, this is the total sums of square, this is the regression sums of square. So total minus regression will give the error. Mean square is actually sums of square divided by degrees of freedom. Mean square is sums of square divided by degrees of freedom. So here for regression mean square, it is sums of square of regression divided by degrees of freedom, because it will have the same value, because the degrees of freedom is only 1. So the same value. Then the error mean square, it is the sums of square of error divided by their respective degrees of freedom. Right? Their respective degrees of freedom. Right? So you can see that error degrees of freedom. The mean square is sums of square of error divided by error degrees of freedom, which is N minus 2. Now F statistics, the ratio between these two, mean square of regression divided by mean square of error. So that is called as F statistics, the ratio. Can you remember in the pool T test we have seen a ratio comparison similar to that. So this is the F statistics. F calculated value can be based on the mean square of regression divided by mean square of error. Right? So this is the basis of the simple ANOVA table. Right, now we are going to do the testing. So when you talk about doing the testing, you have to bring so many things into the mind. First thing is formulation of hypothesis. How to formulate your hypothesis. Second thing, test statistics. Third thing, decision making process. And the fourth thing is conclusion. Right, here also we are going to, using ANOVA, using analysis of variance table, we are going to do the testing. So how to do the testing? What are the hypotheses? So my hypothesis is null hypothesis, beta naught is equal, sorry, beta 1 is equal 0. So what do you mean by beta 1 is equal 0? So if beta 1 is equal positive, that direction, beta 1 is equal negative, that is this direction. If beta 1 is 0, that is the condition like this. So that means there is no linear relationship if beta 1 is equal 0. That is what we are going to test it. If beta 1 is equal 0, there is no relationship. No linear relationship. This term linear is very important, because sometimes you may get a kind of relationship like this, curvilinear relationship, but still you may get beta 1 is equal 0. possible, right? So you'll have to be careful. Just a linear relationship. There's no linear relationship. The alternative is opposite to that. There's a linear relationship where we can say beta 1 is not equal 0. Then test statistics, I have already shown you. The calculated F value can be based on the mean square of regression divided by mean square of error. And based on our calculated value, can you remember our F distribution? This is my critical value, right? This is my table value, F table value. So if any value of calculated higher than the table value, we reject our null hypothesis. So that is my decision making process. Okay, we learn in other T statistics as well. So it is the decision making process. Based on the decision, we can make the conclusion, right? So other way, if it is other way, if the table value is higher than the calculated value, we do not reject our null hypothesis. So we will do with our example, first example, exercise 1. So you have all these summations, the summation x, summation y, summation xy, summation x square, summation y square. We have done that last time also. Right? We can calculate the basic things of beta naught and beta 1. Right? X bar, y bar, and we found the beta 1 also. Beta naught is not necessary here, so we didn't calculate. But summation of certain component is important. Summation xy, summation x square, summation y square, and summation x. All these are necessary. And summation y as well, right? All these components are needed for calculation. I'm going to show you how calculation is there. So beta 1, can you remember in the regression sums of square, beta 1 square multiplied by sums of square of x. Look at the formula. So how we can expand the formula. Right. I will show you some calculation, right? Can you remember we said beta 1 hat square into s x. This is the regression sums of square. This is the regression sums of square. So beta 1, everybody knows what is beta 1. What is this SXX? It is the summation x square minus summation x whole thing square divided by n. So you have all this information, right? If I go back, you cannot come again to the same. Yeah. So this is called as sums of square of x that you can calculate. What is sums of square of y? What is sums of square of y? It is also same as that summation y square minus summation y whole thing square divided by n. So you can find out these values, right? Sums of square of y and sums of square of x. Those are the things that you need, nothing else, right? So this information we got it from our the table, so we can calculate the values, right? So here you see we have all this information, so we can get no problem. Look at this table. So you need this table, right? If you know these two, then we can calculate the error sums of squares. Then, right, now we will fill the table. Degrees of freedom for regression 1, as we said. Total degrees of freedom is 6. Number of observation n is 6. 6 minus 1, which is 5. So 5 minus 1 is 4. That is the error degrees of freedom. Now we can calculate. I have already calculated the value. You also can calculate it based on that. The sum of square for regression is that the total sum of square is 16. So the error sum of square is that. Then we can calculate the mean square because mean square is simply divide sum of square by degrees of freedom. So same mean square as the sum of square for regression. Then error, this is the error mean square. So the F value is that. So this is the important value that we want to use for testing. Right, let's look at the testing value. My calculated value is 5.45. How to look at the table value? To look at the table value, go for the F table value. Take the F table. Take your F table. So here the numerator degrees of freedom, because here mean square regression divided by mean square error. So this is my F calculated value. So what is the degrees of freedom of regression? What is the degrees of freedom of regression? That is 1. What is the degrees of freedom of error? That is 4. Look at the value for 1 and 4. Take the value for 1 and 4. Then you will get the answer. Get the value for 1 and 4. So you will get the answer in the F table. Anyone? What is the value?
7.7.
Okay. Yes, good. 7.71. It is the table value. You should know how to look at the table. This is the numerator degrees of freedom. This is the denominator degrees of freedom. So both degrees of freedom is important. What is our conclusion here? If you look at the distribution, F distribution, this table value is 7.71. So this is the rejecting region. What can you say? The calculated value is much smaller. It is somewhere there. It is smaller than the table value. So we do not reject our null hypothesis. So that our final conclusion is there is no linear. The decision making is there is no linear relationship. We could say as a conclusion, there is no linear relationship between the age and weight. So there is no linear relationship between the age and weight. Okay. So even though our R, what is the R value? Somewhere around 0.75 some value, right? Even it is having a high correlation, but here we come to a conclusion there is no linear relationship between the age and the weight. You see? Right, you can do it for the next set of example also. So you see this is called as scatter plot. Right, you can do it for other this also. It is already done. You can get the answer. Right, I'm not going to discuss that. Right. Now this is a new topic. This is called as R square, coefficient of determination. This is called as coefficient of determination. What is this coefficient of determination? This coefficient of determination is depend on out of total variation, how much variation explained by x, right? So 1 minus sum square of error divided by total sum square. So this can be written as such. This is total sum square, right? Minus error sum square. Total sum square minus error sum square if it is in the table. So total sum square minus error sum square means this we can say it is a regression sum square, right? Sum square due to regression. Divided by the total sum square. So in a formula, we can say, don't forget this. This you should remember. This is not necessary. The above one, remembering not necessary, but you should remember. That means R square, coefficient of determination, is depend on sum square of regression divided by total sums of square. Sums of square of regression divided by total sums of square. This value, R square value, can take from 0 to 1. R square value can be take to 0 to 1, or we can express them in percentage as well, 0 to 100%. If you multiply this by 100, we can take this into 0 to 100% also. Right? Right. Now I will come to that one example. Look at here. This is one model, one set of data where I have fixed for the data I have fixed the regression line. This is another set of data. Another set of data. So this is first example, this is second example. Here I have R square is equal 80%. Here I have R square equal 60%. What can you say about these two models? Where the model is well fitted? Is it in example, I mean, the model 1 or model 2? Where R square is well fitted? Yeah. Yes, the first one, right? Why? Because here, out of total variability, almost 80% of the variability can be explained by X. 80% of the variability can be explained by X out of total variability. So what is remaining? Only remaining is 20% variability. So this 20% variability is actually we cannot explain, which is called as error. In the first model. In the second model, out of 100% variability, 60% could be explained by the X variable. The rest 40% cannot be explained, which is called as error. So now, which model is better? So definitely, model one is better than model 2. Model 1 is better than model 2. Why? Because when the R square is high, that means it is explaining more variability of Y compared to the other models. Right? So here in the first example, it is explaining 80% of the variability. In the second example, it is explaining only 60% of the variability. So whenever the explanation of the variability is higher and higher, it would be better. Right? So quickly take down this. I am going to erase this, otherwise it will coincide with the text. I will give you 30 seconds right now. Right. Now, if you look at the regression methods to be valid, the favoring 4 conditions has to be fulfilled. These are already we discussed about these conditions. If you look at the probability distribution of the error term has to be normal. So what we said is, can you remember earlier when you look at the error terms? So it should produce a normal distribution with a mean of 0 and with the variance of sigma e. So the mean of the distribution is also 0, right? And the standard deviation or the variance has to be constant regardless of x value. So we already said for different x value. So the standard deviation has to be distributed independently but they should have more or less same variance, right? Constant variance, regardless of value of x. This we have already discussed earlier. Then the error of each of these cases has to be distributed normally, identically, and independently. That is also one of the assumptions that we have already taken. So just to remind, so to say that to compare this R stars, it has to have some relationship like that. So now we can test the slope. We can test any value of slope. Before testing, you see, first we can see whether there's a linear relationship or not linear, non-linear relationship, right? Whether it is a no-linear relationship, whether it has a linear relationship between the variables x and y. So here, look at, there's a linear relationship in this case, so that for different inputs of x, we can obtain different inputs of y, right? So we can conclude that slope is not equal to 0. But on the other hand, we can say where here the slope is equal 0, beta 1 is equal 0. So we could say even with the different inputs of x, we get the same output of y, another term, right? So the slope is equal to 0, so that there is no linear relationship. Okay. The testing of slope, we can test the slope. For example, beta 1 is equal 1. What do you mean by beta 1 is equal 1? When x increases by 1 unit, y also increases by 1 unit. That is beta 1 is equal 1. Suppose let's say beta 1 is equal 5. When x increases by 1 unit, y increases by 5 unit. Isn't it? When x increases by 1 unit, y increases by 5 unit. So that is the simple explanation of this beta 1. So we can test this any slope value. Not necessary to test whether it is 0 or not, but we can test, for example, in agriculture. If I increase 1 kilogram of fertilizer, right? Per, I mean, not 1 kilo, 10 kilogram of fertilizer per hectare. If I increase 10 kilogram of fertilizer per hectare, what is the increase? Maybe the yield may be increased by 20 kilogram. Yield may be increased. For example, let's say beta 1 is equal to 20. So if I increase 10 kilogram of, let's say each unit has been split into 10 kilogram. If I increase 10 kilogram of fertilizer, we can increase 20 kilogram of yield per hectare. So likewise, so we can talk about this beta 1 value, different beta 1 value, and also we can test this beta 1 value. So for the test statistics, we are using t-test, right? It's a one sample t-test. It is a one sample t-test. This is the predicted value coming from our model. We can test it. Let's say in an economic study, this is the input, output. So if I increase x by 1 unit, how much output increase in y? So let's say beta 1 is equal 2.2 as an example. That means if I invest 1 rupee as an input, if I invest 1 rupee as an invest, I can obtain, let's say this output is a profit, I can obtain 2.2 rupees as the profit. So we can use it then, right? And also we can test it. So this beta 1 need not to be 0. It can be any value. And this is the standard deviation for the beta 1 that is based on standard error of beta 1 that is based on this is based on our mean square from the ANOVA table. Mean square error from the ANOVA table. Take the square root of mean square error. That is SE divided by square root of sums of square. This is basically called as sums of square. Right? So this formula you can realize and do the testing. But the degrees of freedom, it is the error degrees of freedom. Look at the ANOVA table. So this is the error degrees of freedom we always use for looking at the table, T table. We are looking at the T table, T statistics. So that for that you have the degrees of freedom n minus 2. Similarly, we can interpret and test beta naught as well. Some value. Look at here, the age and weight of animal or human beings. So when you say weight at the age of 0, when you say weight at the age of 0, that is actually birth rate. Isn't it? That is actually birth rate. Age at weight at age of 0, that is actually birth rate. So we can find out what is the average birth rate. Okay, so we can use again the test statistics. This is the T calculated value. Again, the degrees of freedom is error degrees of freedom. Similar to earlier one, this is the predicted value. This is the hypothesis value. Any value, hypothesis value can be put it here. And this is the standard error of the estimate. So this we know what it is. That is the square root of mean square error into square root of 1 over n plus x bar square divided by sums of square. So you know what is sums of square x. I have already explained. So you can test it any value as you like, if you wish. Right. Next, we will come to the confidence interval. When you talk about confidence interval, let's say this is the predicted line. So let's say this is x bar, this is the y bar, x bar and the y bar. Normally, if you draw the predicted line, if you draw the confidence line, confidence interval, for each of these observed value, we can draw the confidence interval. So usually the confidence interval is like this. So the shortest confidence interval coincide with the x bar and the y bar. Shortest confidence interval coincide with the x bar and y bar. Then on the both side of x value, the confidence interval is increasing. So you see here the confidence interval is very high. Here also confidence interval is very high. So in both sides the confidence interval increases. So that is the principle. I will show you with an example. Confidence interval estimates the average y for a given x. Confidence interval estimates the average y for a given x value. So average y value for a given x value. So that is important, right? Erase it. Then this is the formula that we can use it for confidence interval. Any level of confidence interval, 95% or 99% or any level of confidence interval can be approached. So it is the y hat plus or minus. So this is the predicted value plus or minus the t table value. This is the alpha by 2 n minus 2 degrees of freedom. Then the SE, that is the square root of mean square, right? Square root of mean square error. Then square root of 1 over n plus xg minus x bar whole thing square. What is xg here? This is what xg for a particular value. This is y hat, right? So this y hat is actually this one. So xg for a given x value only you can predict the y value. So this is xg minus x bar. X bar is the overall mean. So this is x bar, right? Divided by this is sums of square of x. This is actually sums of square of x, right? Right. From exercise 2, we will take a predicted value for an age of 25. So this is my formula. This is my predicted equation. I can simply substitute of 25 here and get the value as such. So at the age of 25 years, on an average, we are having blood pressure 123.5 millimeter per mercury. So that is the example that I took. So now I'm going to look at the confidence interval for this value. Confidence interval, because this one value we cannot just justify. So we'll have to find out how 95% confident that I can say the blood pressure is ranging between these two values for a given age, let's say 25. For that, we can use the formula, the same formula. Now we can substitute the value. The predicted value is 123.5 plus or minus. This is the table value, right? N minus 2 degrees of freedom. N is 20 in this example. So 18 degrees of freedom. Look at the two-tail value. Then we have square root of mean square error. That is the value from the table. Take it out. Then 1 over n plus this is 25, the age of 25, xg minus x bar square, whole thing divided by this is sum square of x. So you will end up with some value. So how we can interpret this? This is the range of value that you come across, 121.7 to 125.3. How you can interpret this? This is how you can interpret the confidence interval 95% for the mean estimate of blood pressure at the age of 25 years, which is ranging from 121.7 to 125.3 millimeter mercury, right? This is how we can interpret the value. Confidence interval for a predicted value. Any questions? Confidence interval for predicted value. So you first find out the predicted value. So that is the predicted value. Now you find out the confidence interval for that predicted value. So using the same formula. So you can find out the values from earlier table and get the. Right, now I'm going to show how this confidence interval changes for different x values. Earlier I have shown you some graphical explanation. Now I'm going to show how this is feasible. Right, so this is the formula. Right, so at the x bar, closer to the x bar, or at the level of x bar, the interval become smaller. So that means at the shortest interval, you can find out at the x bar. If you go away from x bar, the intervals become long. So as I pointed out earlier, right? Let's say this is x bar, this is y bar, x bar. So the interval is shorter at the level of x bar. So here the interval is shorter, where the interval is longer if you go either way, above the x bar or below the x bar. So this is what we are going to look at it. right? So I will erase this, otherwise confusing. So this is my predicted equation for a given x value, right? So this is my x bar and this is y bar basically. So when xg is equal x bar, when xg is equal x bar, this component is missing. So if this, I mean, this is become 0. So this component becomes 0 when xg is equal x bar, right? So if that component becomes 0, then that is the case. That is the confidence interval based on this calculation. So that is the confidence interval, the value of higher and the lower value of y. Now similarly, you can take some value plus one value and minus one value from the x bar. Take some high value and the low value. So if you take the high and the low value, definitely it is square. So no problem. I'm not cancelling off the high and the low value. Now it will impact on our y hat value as well, so that the distance become more if you go away. Similarly, if you go for the second point of the value, that is plus 2 and minus 2, right? So the calculation will be 2 square. So this component become larger and larger. The value become larger and larger. So likewise, at last you can say the confidence interval is as such. So the shortest confidence interval, you can find it here at the x bar, and if you go away from x bar, you can see the confidence interval become wider and wider. Right. What do you mean by interpolation and extrapolation? Look at here, this data. I will go in the so I have, let's say I have data from 2 to x value 2 to 10. Just take example. So these are observed value. Observed values are the x range is from 2 to 10. The x range of value is 2 to 10. Right? If I want to predict a value, I can predict a value at any x point in between these 2 and 10. So I can get the predicted value here. I can get the predicted value there, and so on. I can get the predicted value there, for example. I can find out, no problem. So that is called as, so this is within the range of x value. So that is called as interpolation. So if you have the data, right, of any x value that you predict the y value within the given x range of value, then it is called as interpolation. What do you mean by extrapolation? Look at here. Now I want to predict a value at the x equal 50, at the value of x equal 50. So what I want to do is I am expanding this line and look at the value 450. So this is my value. This is my value, right? So let's say y x, right, at the y15. I will put it as y15. So this is my value. Now what is our problem? Let's say we have expanded this predicted line. We cannot say anything about our x value beyond this 10. So suppose, let's say my actual plot is something like this beyond this, because we didn't measure anything. For example, temperature. Here temperature, yield. You have measured only within this range of temperature, 2 to 10 degrees centigrade. So 2 to 10 degrees centigrade, temperature favor the yield. But after, let's say this is 45, temperature 45, what is happening? So it is decreasing, the yield is decreasing. So beyond this point, because this is the only point that we access to the data. So beyond this point, we don't know how the data is behaving. Therefore, what will I have to do? If you predict the value at the temperature of 45, we have a problem. So we will say yield is this much. But actual yield cannot be that much because yield is not linear beyond a particular point. So beyond this particular point, yield is not increasing. So this is because of the term called as extrapolation. This is called as extrapolation. This is called as extrapolation. So interpolation is always better. It is safe. Within the data, we predict the value. Extrapolation means beyond the data available, we try to predict the value. So extrapolation is always dangerous. So this is what we call as extrapolation. So beyond the x value, we try to predict the y value. Outside the range of the data, we try to predict the value. So this is a danger in terms of prediction. So that is called as extrapolation. Right? The x and y points also, this is the explanation of extrapolation. So this is these 2 points are lying outside the range of the data. So this is not a good practice. Extrapolation is not a good practice. So we'll have to always adhere to the interpolation. Right. Now look at the outline for a situation. Outlier, look at the outlier. So no outlier, the regression line is fine. So now see, there's a very simple outlier. What has happened? Beta naught is not changed from black to blue color because of this outlier. But what is happening for beta 1? Sorry, beta other way around. Beta beta 1, no changes. No changes in beta 1. Right? Why? Because the slope is same in both cases. What about beta naught? There's a change, isn't it? There's a change because this is connecting to different positions. So difference is there. So the outlier will make influence. Look at the second outlier. It is okay, some outliers are very serious. Now this, because of this outlier, what has happened? Both change, beta naught and beta 1. Both have changed in this particular example. So you have to be careful about this outlier. When you do this regression line, you have to plot and see first. First, you will have to plot and see like this. Suddenly you have a point here. So that means something wrong with this, right? It is not behaving with other data. Then it is something wrong here. So we'll have to identify, and if possible, we'll have to remove it if necessary. So outlier, we talked about outlier, another box plot, right? Right. The normality of the error term that we have learned, right? This is the mean with a 0, and it has a normal distribution as such. So this is this has to be like this, right? Suppose if you have a situation like this, so this is the mean. So there is nothing called normal distribution, right? So it has to be something like this. So this is normality. No, this is if you don't have that kind of feature, then we call it as non-normality, right? Check for the normality. Nowadays, we have a lot of softwares, so we can test for normality. If there's not normality, we'll have to do some kind of transformation of the data. When you do your final year research, sometimes you may have to do transformation if it is not properly designed. Right. The next one is called as heteroscedasticity. Heteroscedasticity means, can you remember? We discussed about different variants at the sorry, x1, x2, x3 variants at variants. You can draw it. So variance at different places. So when you talk about sigma 1 square, sigma 2 square, sigma 3 square. So all sigma 1 square is equal sigma 2 square equal sigma 3 square. So this is called as homogeneity of variance at every level of x. So this is one of the assumptions. So if something wrong, if these are not equal, then it is called as heteroscedasticity condition. So heteroscedasticity, look at here. So this is when the predicted value increases along the x-axis. You see here, the variability of the residual also increases. You see, variability of residuals also increases with the increase of predicted value. Right? So this is called as heteroscedasticity. We'll have to do some transformation on the data. By plotting your residuals and the predicted value, we can find out this. Normally nowadays all software can give this kind of plots. See an example here. So if you look at this case, here we could say no heteroscedasticity. Why? Even if you increase this is the predicted value. If you increase the predicted value, there's no any pattern of the error terms. Error terms remain as it is. So this is a good data. You don't need any transformation. You can use the data directly to do the regression analysis. So here, actually, no heteroscedasticity. No heteroscedasticity. Right? Right? Any questions? So today I'm going to stop with this. We can continue next time. I will fix another date for my last lecture. So I need another 1 hour so that I can finish. Any questions?